gives free energy and E cells. So gives free energy. So how can you write the equation for the Gibbs free energy for cells? So here the maximum cell potential, so that is directly related to the free energy. So there is a difference between the reactants and the products in the cells. We know that. What is that the cell potential? Cell potential, it is directly related to the free energy, and which is a difference between the reactants and the products in the cells. Then how can you write it as in the equation? So the mathematical expression for the Gibbs free energy, we can write it as, see this one. So this is delta G naught is equal to minus NF E naught. Delta G naught is equal to minus NF E naught. So this is a Gibbs free energy equation for the cell. So here delta G naught means Gibbs free energy, and where N means, here N means number of moles. See here, number of moles transport per mole of a reactant and products. And here what is the F? F means it is Faraday. Yes, we know that. Faraday, what is the value of the Faraday? So that is equal to 96,500. We are taking the value as a 96,500 coulombs charge per mole of electrons. And here it is E naught. E naught means it is a volts. So I can write the equation for the volts. So that is E is equal to work by charge. So this is a Gibbs equation, Gibbs free energy equation for the cells. So delta G naught is equal to minus NF E naught. So here it is some relationship. What are the relationship presence in between the E naught cell and delta G and K? That means relations which are present in between the E naught and as well as free energy and also a constant. That means K. Yes, we know that what is the relationship which is present in between the Gibbs free energy and cell potential. So earlier we know that is equal to delta G. See this one. Delta G naught is equal to minus NF E naught. Yes, we know that. What is the relationship? This indicate the what is the relationship between present in between the Gibbs free energy and cell potential. Yes. Yes, we know that in this N is the number of electrons transferred in the balanced reaction, and F is the Faraday. So that is value is approximately is equal to 96,500, and the charge on the mole of electrons. Now here, the standard free energy change of a chemical reaction is also related to the, so that is equilibrium constants. See this, that is equilibrium constants for the reaction. So that can be shown in the below the reaction. So here, so this reaction, see this reaction, it is relationship between the Gibbs free energy and cell potential. Now coming to the what is the relationship between presenting between the free energy and equilibrium constant? So that is K. So that is K. That means here also the free energy, the change of a chemical reaction is also related to the equilibrium constant for the reactions. So it is see this. So this is a relationship between the free energy and equilibrium constant. So that is delta G naught is equal to minus RT log K. What is the relationship? So that is delta G naught is equal to minus RT log K. So that is equal to minus 2.303 RT log K. So this is exponential logarithm. So if you convert into a base logarithm, then you can write it, you can multiply with the value that is 2.303. So here what happened, delta G naught is equal to minus RT log K is equal to minus 2.303. So conversion, if you convert the exponential logarithm into base logarithm, then you can multiply with the 2.303 value. So that is minus 2.303 RT log K. So in this equation, R is the gas constant. Yes, we know that T is the temperature in Kelvin. That means our total temperature. E naught means see. So here it T is temperature. Yes, yes, we know it. Now, then what is the relationship between present the the cell potential as well as the equilibrium constant? So what is that relation which is present in between the E naught and that means cell potential and K? Now here also the E naught is also related to the equilibrium constant. So then from the equation, see here, from these two equations, see this one and this one. From equation this one and this one, by taking the two equation, then we can easily write the what is the relationship between present in between the that means cell potential and the equilibrium constant. So here by taking these two reactions, so you know it is minus NF E naught is equal to what is that minus RT log K. Yes, we want to write the equation for the E naught, then E naught is equal to take the total NF. NF means minus minus cancel. Then RT by NF log K. Yes. So this is a relationship. Okay. Then finally we can get this type of relationship. See this one. This is a reaction. So this reaction, it is indicated the relationship between present in between the E naught and equilibrium constant. So by using these two equations, then you can write this equation. So there is E naught is equal to RT log K by NF. So this is an exponential logarithm. Then convert the base logarithm. You can multiply with the value that is 2.303. Then we can get the value that is 2.303 RT log K by NF. So this equation, see this one. So this equation it gives the relationship between the E naught, that means cell potential, and equilibrium constant K. Now here in this equation, if you substitute all the values, so that means T and R and F, T or F, or if you substitute these constant values in this equation, then we can get a simplified equation. So here it is the simplified equation after substituting the values of R, F, and T. So this is a simplified equation. So that is E naught is equal to 0.0592 log K by N. So this is a simplified equation after substituting all the values of N and F or. Yes. So this is simplified equation. So this is also you can use it in the problematic questions. So here this equation also gives the relationship between the E naught, see E naught and K, cell That means equilibrium constant. But under the non-standard conditions here in the laboratory, under non-standard condition, it is possible to calculate the actual value of the cell EM. So there is E. Then how can we write a equation under the non-standard conditions? So here in the under non-standard conditions, so the nearest equations. Then what is the nearest equation? So here it is the nearest equation. So that is E is equal to E naught minus 0.0592 log Q by N. Yes. Next we know that what is the nearest equation. So here Q means question. Question means is question. Question means is it give it related to the concentration of the reactants and products. Humans. So these are the some equations which give the information about the relationship of the cell EMF. That means cell potential, free energy, and equilibrium constant. So it is very important. So these are the relationships. So these relationships. So regarding about the E cell, that is cell potential, and free energy and equilibrium constants. So next one, so that is potentiometric titrations. Potentiometric titrations. So likewise, like conductometric titration. So in the conductometric titration, what we had done. So by using the conductance values, see here, by using the conductance values, then we can easily determine the what is the end point, that is equilibrium points of two solutions. So in that case, in the conductometric titrations, that is based on the conductance values. Based on the conductance value, then we can easily find out the what is the end point or the equilibrium point of the both the solutions. So in that case, that is with respect to the conductance value. So likewise here also, potentiometric titrations means we are taking the EMF values. So based on the EMF values, then we can easily find out what is the equilibrium point and our end point of the solutions. See the difference between the conductometric titrations and potentiometric titration. Now, both are nearly same. In the conductometric titrations, we are using the conductometry. That conductometry will give the conductance values. Here we are using the potentiometer. Say potentiometer. By using the potentiometer, we can easily find out what is the end point of the solutions. So here, what is the principle? What is the principle which is present in the potentiometric titrations? So coming to the principle, the EMF of a cell, so that is depending upon the concentration of the electrolytes. So EMF, the electromotive force of a cell, EMF means what is the EMF? The difference between the potential difference between the two electrodes. So there is known as EMF. Yes. So EMF of cell, so that is depending upon the concentration of the electrolytes with which the electrolytes are in contact. So therefore, the electrode reaction is, yes, we know that the electrode reaction. So it is Mn plus N electrons. So that is equal to M. So this is a cell reaction, that means electrode reactions. Now in this case, as the concentration of the Mn plus changes, then automatically the EMF of this cell is also changed. That means we know that. So here you observe that the EMF, the EMF cell, So that is depending upon the concentration of the electrolyte. So remember this one. Okay. If there is a change in the concentration of the electrolyte, then it will automatically change in the EMF of the cell. Okay, that is the principle. So here it is the potentiometer titration setup. So this is a setup, potentiometer titration setup. So in these potentiometer titrations, which operators are present in the potentiometer titration? So let's see. Let's say one look at this picture. So here is that is burette. So see this one. This is a burette, and this is a beaker. See this is a beaker, and this is an electrode. See this. So this is a reference electrode. See this is a reference electrode. And what is this? So this is indicator. So this is indicator electrode. So this indicator will act. This electrode will act as a indicator electrode. So this is a indicator electrode. So what is this? So this is a reference electrode. So commonly we are taking in the potentiometric titration. That is, yes, we know that this is a calomel electrode. So in this titration, the calomel electrode will act as a reference electrode. What is a reference electrode? Non-potential value. We know the potential value of the or EMF of this reference electrode. Okay. So both the electrodes are connected to both the reference electrode and this indicator electrode. Both the two electrodes are connected to the potentiometer. This is a potentiometer. This potentiometer will give the EMF of this indicator electrodes. So this is the total setup which is present in the potentiometer radiation. This is a burette. So here it is a indicator electrode. That means what we are going to determine the EMF of any solution. So that can be taken in this beaker. So this is a potentiometric titration setup. So in the setup, what is it? The burette is present and a beaker which is consisting electrode. So that will act as an indicator electrode, and it is connected to the one reference electrode. Here is the reference electrode. It is a calomel electrode. Calomel electrode will act as the reference electrodes. So both the electrodes are connected to the potentiometer. Yes. Potentiometer. So this is a setup. So now here the potential titration involve the measurement of series. Yes, we know that the potentiometer and potentiometric titration show they will give the values of EMF. So this titration involves the measurement of EMF between the reference electrode and the indicator electrode. See this one. They will give the reference, the EMF values between the which is present in between the reference electrode and the indicator electrode. Reference electrode means the calomel electrodes, and the indicator electrode means what we are taking in the process. So that will act as a indicator electrode. So the potentiometer radiation, it gives the relationship. That means it gives the EMF values, the EMF which is between the reference electrode and indicator electrode. So with the addition of the titrant which is present in the burette. So here some type of potentiometric equations are present. So what type of potentiometric equations are there? See here. So majorly these potentiometric equations are classified into three categories. So first one is precipitated titrations, second one is redox titrations, and third one is acid-base titrations. So let's see one by one. First one is precipitation titrations. So in this precipitation titration, the best example for this, it is silver-nitrate versus NaCl. Silver-nitrate versus NaCl. So in the potentiometric titration, in the first one, so that is a precipitation titration. So here, NaCl, see this one, the NaCl, it is taken in the burette, and silver nitrate, see this one, silver nitrate is present in the beaker, and here it is a silver electron. See this is a silver electron. Okay. So here, how can you do the potentiometric titrations between the silver nitrate versus the NaCl? So here, the known amount of a silver nitrate solution is taken in the beaker. Yes, we know that, and the indicator electrode. That means silver. The indicator electrode here, it is the silver ion electrode. So that is also placed in it. Okay. So that will act as a indicator electrode. What is the indicator electrode? Is the silver ion electrode. Silver electrode which is present in the silver nitrate solution beaker. Okay. Then it is connected to the reference cell. That means calomel to form a galvanic cell. Yes. So that will act as a galvanic cell. Yes. So after set up this one, after connecting the both the indicator electrode and calomel electrode to the potentiometer. So then the cell is then connected to the potentiometer and its E cell, and E cell is determined. So by adding the NaCl, see here, by adding the NaCl which is present in the burette to the silver nitrate which is present in the beaker, then after adding the NaCl, then it will give the what is the EMF, what is the EMF difference value, so in between the reference and this indicator electrode. So the values, so that potentiometer will show the values of the EMF. So this way, while adding the continuously, the NaCl which is present in the burette with silver nitrate, then we can write the what is the difference value, so which is coming from the potentiometer. So here, then what happened after? So when the silver nitrate solution is titrated against the standard Na solution, so taken in the burette, in the burette, which solution is present? Sodium chloride is present in the burette. So then the EMF is going on decreases. See, so first the EMF value. After adding the NaCl, there is a continuously decreasing values. It will show, the potentiometer will show the continuously decreasing values. So this is because of the decreasing of the silver ion concentration. See this one. While adding the NaCl to the silver nitrate solution, there is a, see this one, the availability of the silver ions are gradually decreases. So because of that, the EMF values are gradually decreases. So here, what type of reaction is take place? See this one. After adding the NaCl solution to the silver nitrate, see here, silver nitrate will react the NaCl and it will give this type of products, that is silver chloride plus sodium nitrate. So all the silver ions are converted as silver chlorides. So because of decreasing in the silver ions, they're also decreasing in the EMF. Because the principle is the EMF of the cell, it is depending upon the concentration of the solution. Already we discussed in the first one. Yes. So after endpoint, what happened? At the end point, the EMF is suddenly decreases. So suddenly decreases. So after the end point, there is a no noticeable change in the potential. So after completion of this potentiometric titration, so we can draw a graph between the EMF, between the EMF values and the value of the NECL. Then we can get the this type of graph. See this one. So this type of a graph. So this is a graph between the EMF value versus NECL. That is the value of the NECL. Okay. Yes. See this one. So gradually decrease. So here this is a equilibrium point. So there is end point. This is indicate the end point. If you want to clear an end point to this potentiometric titration, then we can draw a graph between the delta E. See this one, the product of the delta E by delta V, the magnitude of the delta E by delta V versus value. Then we can get a sharp end point. So by using this graph, we can easily find out what is the sharp end point. So this is a, if we want the sharp end point, then we can you can take the this type this value. So that is the delta E by delta V by versus value of the NEC. So by using these two graph, then we can easily find out what is the end point. So this is a graph about the precipitation titrations by using the potentiometric titrations. So here the graphs here, when the EMF is plotted against the value of the NECL, the curve of a type shown in the figure, yeah, already we seen that. The endpoint, see this. So the endpoint is the one where the slope of the curve is maximum. See this one. So this is okay. Slope is the maximum. So that is endpoint. Then the graph, see this one. If you want to do the clear cut endpoint, then we can draw the graph between the delta E by delta V versus the NECL. So to get the accurate, so to get the accurate the endpoint. So the second reaction, so there is reduction titrations. Reduction titrations. So the best example for the redox titrations. So that is iron sulfate versus potassium dichromate. See this one. The best example for the redox is iron sulfate versus potassium dichromate. So how can you do the redox titration through by using this potentiometric titration? So see here, known amount of a iron sulfate system. The known amount of a iron sulfate is taken in beaker. In a beaker. So and the indicator electrode here is a, what is the indicator electrode? This is platinum electrode will act as the indicator electrode. Here it is. So in the beaker, which solution is taken? There is iron sulfate. That is ferrous sulfate is taken in the beaker, and in the beaker we can keep the electrode. So that is platinum electrode. That platinum electrode will act as the indicator electrode. Okay, then. So it is then connected to the reference electrode generally. So that is calomel electrode is act as a reference electrode to form a galvanic cell. Then these two cells are connected to the potentiometer, and then E cell is determined. So here the same experiment. So while adding the iron sulfate solution, which is here potassium dichromate, see this one, the potassium dichromate is present in the burette. So which solution is present in the burette? Burette potassium dichromate is present in the burette. While adding the potassium dichromate, which is present in the burette, to the ferrous sulfate, which is present in the beaker. If you add the potassium dichromate to the iron sulfate, which is present in the beaker, then it will give the what is the EMF difference, EMF values. So while adding the potassium dichromate solution to the iron sulfate, then we can note down the what are the EMF values. So that are coming from the potentiometer. So these are the graphs which are obtained from this redox titration. See here, after completion of the titration, then we can draw a graph between the EMF. See this one, the EMF versus potential diagrams. So by observing this graph, you can understand that while adding the potassium dichromate solution to the iron sulfide solution, there is a gradually increasing. See this one, gradually increasing in the EMFs, gradually increasing the EMFs values. So this is a end point. This is the end point. If you want the sharp end point, then you can draw a graph between the delta E by delta V versus potassium dichromate, the volume of the potassium dichromate. Then you can get the a sharp end point like this. See this one. So this is a the peak. See this one, the peak. It is indicate the end point of these two solutions. So this is about the redox titrations. The process is same. So after completion of the titration, then you just draw the graphs between the EMF versus EMF values which are obtained from the potentiometer and the volume of the potassium dichromate. Or if you want the sharp indicator or accurate end point, then you can draw the graph between the delta E by delta V versus potassium dichromate. So this is about redox titrations. And coming to the third one, so that is last one, acid-base titrations. So here, so this type of potentiometer titrations is used to determine the concentration of a given acid or base by neutralizing it exactly using a standard solution. See this one, by using the standard solution of a base or acid. Standard solution means, yes, we know that the whose concentration is this. So by using the known concentration, so by using the known concentration of the any one of this acid or base, then we can easily find out the what is the concentration of the unknown acid or base. So this way we can easily find out the end point by using the potentiometer. So in the acid-base titrations. So here the same acid is taken in the beaker and base. So the base solution, it is taken in the burette, and these two cells are connected to the potentiometer. That means calomel electrode will act as a reference electrode. Here it is a platinum or whatever electrode is taken in the acid solution, that is which is present in the beaker. So that will act as a indicator electrode. So both these two electrodes are connected to the potentiometer. So after connecting that, if you add the acid, if you add the base, so that is which is present in the beaker to the acid which is present in the beaker, then potentiometer will expose the different type of EMF values. Then note down that values after completion of experiment, then you can easily draw the graph EMF versus volume of the base, volume of the base which is present in the burette. See this one. So after completion of experiment, then you can easily draw the values which are obtained from the experiment, that is EMF values versus base. Then this type of graph will obtain. So by using this graph, so this is this one, the slope. So this indicate the end point, indicate the end point or equilibrium point. If you want the sharp end point, then you can draw the graph between the delta E by delta V versus volume of base. then you can get the curve like this. See this one, this is delta v, delta e by delta v, and this is the volume. Then you can get this type of graph, and this peak, this is a peak. So after drawing a line from the peak, then so this indicate the it is the equilibrium point or end point of the these solutions, these two solutions. So this is about the acid-base titrations. So this is the potentiometric titrations. So by using the potentiometric titrations, then we can easily conduct this type of different type of titrations, that is precipitation titrations and redox titration, acid-base titrations. So in this all the titrations, so the main thing it is the setup is already same. So this is a setup, that is a burette and a beaker and electrode, that is suitable electrode. We are using the solution which is present in the beaker. Then we can use the suitable electrode. So that electrode will act as a indicator electrode that connected to the calomel electrode. That means a reference electrode through the salt bridge. Both the electrodes are connected to the potentiometer. All the setup is same. And after completion of titration, after completion of this experiment, just you can draw the values, the EMF values which are obtained from the experiment, that is EMF versus the volume of solution which is present in the burette. Then you can get the easily the end point of the these solutions. So this is about potentiometric titrations. So this is a main topics which are present in the electrochemistry. So just one look at potentiometer titrations are important, and the relationship between E naught and delta G, Gibbs free energy, and electrochemical series. What are the electrochemical series and its applications, Nernst equation and its examples, and also electromotive force and its equation, and reversible and irreversible cells are important, and the reference electrodes, calomel electrodes, construction of calomel electrodes, and reactions, cell reactions, hydrogen electrodes, single electrode potential, and Daniel cell construction and cell reactions, representation of cell, conductometric titrations are important. Different type of conductometric titrations, acid-base titrations are important, and transport number and HITARP method, that is the important one. HITARP method and transport number. How can you calculate the transport number of ion by using the HITARP method? That is the important one. Cold-Rush law. What is Cold-Rush law and its applications? The application, this is degree of dissociation is important. And next one, that is determination of equivalent connections of the weak electrodes by using the strong electrode. That is the important one. And Debye-Uckel-Ansager equation and Debye-Uckel theory, one of the important theory. Two effects are present: relaxation and electrophoric effect. This is the important one. And Ostwald theory, Ostwald dilution theory and its limitations. That is the important one. Arrhenius theory and its application, its limitations. That is important. Degree of dissociation and various definitions: molar conductance, equivalent conductance, specific conductance, conductancy, resistancy, electrolyte, different type of electrolytes, and what are the conductors, different type of conductors. So this is about the electrochemistry. So this is one of the important chapter in the physical chemistry.